So, the second part of this talk will feature primarily rotation, what are they, what do we do with them, and so on. Okay. So, how can you get rid of that? So कैसे हटाएं? Okay, it's not a very significant thing, it's just hiding the title of the slide, so let's move on, okay? All right, so in the previous slides you saw we were talking about the man optimal matching, and the example that I was using this matching mu0, which was the man optimal stable matching. Now I'm going to start with another match. It's also a stable matching, but it's not the man optimal stable matching. And I'm going to define this object called rotation with respect to this. Now what I want you to understand is you can define rotation with respect to any stable matchings. Okay? And the definition is constructive. We'll talk about how to find such rotations, and then we'll get to what to do with these rotations. Okay? So the rotations are constructed in the very sort of way that they use this thing that we did for the extended Gale-Shapley, where we basically created this GS lists, the pruned down, shortened preference list for the men and the women. Okay? So given a stable matching mu, so I'm sorry, the animations here are a bit off. This just focus on the definition right now. Okay? For a given stable matching mu, for each man M, we define two functions with respect to this matching mu. One is the successor function and another is the next function. S is the successor function. Okay? So each man M looks at his preference list and sees the first woman who is behind his, who is less preferred than his current partner in the matching mu, but who prefers him to her current partner. Is it clear? So this definition would make sense even if I didn't talk about extended Gale-Shapley. But what does extended Gale-Shapley do? Extended Gale-Shapley basically proves the preference list from the men's perspective in a way that the successor woman is literally the person who is right behind his current partner. That's what we saw, right? The only people who are retained are women who prefer this man over their current partner. So the successor is the woman who is right after his current partner, okay? And the current partner sits at the top of his preference list. We define this for every man. Now notice the same woman can be multiple men's successor. So that's fine. Okay? We are just saying this is a function. I'm not saying it's a one-to-one function or anything, or a non-to function. It's just a function. It's clear why it's a function, right? Now the next function points to the mu partner of the successor woman. Is it clear? So next of M with respect to the matching mu is the mu partner of the woman who is the successor of this man M. Okay? So basically the woman who is sitting right behind my current partner, her mu partner is the next function pointing to. So in this example mu1, let's just see what this thing is. So right now mu1, in mu1 matching man M1 is matched to W8. So that's, can you see that the underline that W8 is his current partner, okay? So who should be his successor? Is it? A successor is the woman who is right behind his current partner. W3, exactly. So for M2, who is the successor? Correct, because the person who's right, that person has already been dropped from the GS list, it's actually W6, right? And now I can go to the women's preference list and see, well, who is the new one partner of W8? Well, it is M1. So therefore, the next function for M1, sorry, the new partner of W3 who is a successor is M2. So that's M2 is M1's next the outcome of the next function. Okay. So now if I tabulate this, this is the relation I get for each man. Clear? So you'll see that there are some women like W5 for example, who is both M6 and M7 successor. Right? So naturally her partner M3 is M3, M6 and M7's next function, right? So that can happen. Now looking at this, now I try to find this. So now imagine I'm just wondering if, yes. So rotations are a bunch of a subset of the matching pairs where a certain cyclic property holds. So your successor, you collect all the successor functions. So M0, if you can read it, M0, W0 are matched to each other in the current matching. W1 is M0's successor. Therefore, M1 is M0's next. W2 is M1's successor. Therefore, M2 is M1's next, and so on. You do this until this whole thing comes back to where you started, or at least one of the pairs repeats itself. Okay? So this next and successor property if it allows you to find a cycle, if there exists a cycle, then that is a rotation. Is it clear? Okay. Now, if this is a property that is at the heart of everything, it's like the first key step, that if this instance has more than one stable matchings, meaning the man optimal matching is also not the woman optimal matching, then you know you have at least two distinct matchings, then there will be at least one rotation in the man optimal stable matching. And there will be a rotation in the man optimal stable matching means in this way. So if I look at this set of the matched pairs in the man optimal matching, there will be a subset of pairs which will satisfy this cyclic property. When this happens, we say that this rotation is exposed in this matching. Okay? So just terminology so far. Why can you show this? Like, what is the argument for this? That if there are at least two stable matchings in the given instance, there should be at least one rotation exposed in the man optimal matching, man optimal stable matching. If you recall the main points of the first lecture, this should be clear. We said something about the GS lists. We had that. Okay. Okay. You are saying that there are no. Okay. So what we are actually referring to is that the GS list contains all the stable matchings. So if there are at least two stable matchings, the man and the woman optimal stable matching at least, and maybe there are others, they are both in the GS lists, right? The GS list, if such a thing is true, from the GS list we define this rotation, right? So starting from the GS list, we define the next and the successor functions. Now the question is, so the next and the successor functions are defined on the GS list. There is a man optimal starting with a man optimal stable matching. I define the next and the successor function. and there is a woman optimal stable matching. The question is, why should there be a rotation exposed? Like, you can have the next and successor function, but why should a cycle such as this exist? So that's the key point here. Any guesses? Yes?
If the cycle is stable matching, then it infers that the rotation from one stable matching will lead to another.
You're claiming that, like, say that again.
Under the presumed structure that there is a cycle amongst the stable matches, even if there's only two, a rotation, an n number of rotations from the first stable matching would have to lead to the second stable matching.
Is that obvious to you?
I mean, it seems intuitively inherent. Not obvious.
That's what, so basically anytime I expose a rotation and I eliminate, yes.
It maybe creates some instability in the cycles. Ma'am, identification maybe create any what I can say instability in the cycles or in the matching process maybe.
You mean if I change the people who are participating in this sort of cycle, if I change their partners around, it can create instability?
Yes, ma'am, maybe.
If you see this definition more closely, that is the thing that does not happen. Why? Because the next function is defined with respect to a woman who likes this man, this person who is sitting next to her, the adjacent pair, more than her current partner. So if that man gets shifted to this woman, the women, nobody is going to form a blocking pair. Because when we shift along the cycle, let me just give this thing away, then in the rotation when I sort of switch the pairs along, all the women have a strict improvement. That's what the successor thing is, right? That the women who is my successor likes me strictly more than her current partner. So all the women improve, all the men go down, their preference value goes down. And everybody else remains the same. Don't touch it, I just eliminate that cycle, I just rotate around that cycle, right? So if there were no blocking, so none of the women are complaining because they have a strictly better partner, so there are no blocking pairs. That's basically what happens. But we are just moving along a little, I just want to point out, yes?
It is achievable in every case. Isn't the rotation is achievable in every stable match?
So this is basically trying to say, this, property basically says that if you have at least two stable matching, there will be some rotation exposed in the man optimal stable matching, right? I have not said anything more than that. I have not said anything about what happens with an arbitrary stable matching. Are there rotations, not rotations? I have not said anything. This definition is purely constructive. Like it is saying there is a matching here, define the next and successor pairs. If you find a cycle like this, call it a rotation. That's it. It's like an abstract definition. What we do with it is all left to be said. Okay? All right. So, the yes?
So if there are more than one rotation possible, should we have such kind of a hierarchy in the rotations?
You tell me, what do you think given all that we just now discussed?
I guess there has to be some optimal kind of rotation. But it will be different, like it depends on what we are defining as an optimal one.
Right. That is the correct answer here. As such, if two or more than two rotations are simultaneously exposed in a matching, it should not be very hard to see that they have to be vertex disjoint. Is that easy to see? Okay, suppose it is vertex disjoint. So what that means at least is that I can do this rotation operation, elimination, going around the cycle with one rotation and the other one simultaneously or step by step, like neither one interferes with the other if they are vertex disjoint, right? So as such, I could operate on each one of them and I would get a new matching. So that in and of itself does not tell me whether one matching is better than the other matching. But as you're saying, there might be some other objective that I'm trying to attain, and that tells me that no, don't eliminate this rotation, eliminate this rotation because then you might be able to attain that outcome faster or easily than going the other way. I'm talking about the directed graph formed by this next and the successor this thing. So, okay, so I am actually going to get there. I'm going to define precisely what I mean by which graph and so on. As such, right now what I was saying is that there is an edge between all the matched pairs, obviously. There's also an edge between this guy M0 and W1 because W1 is in M0's preference list, right? So, there is an edge. You can think of it as a direct, so the cycle is basically M0, W0 matching pair edge. From W1 to, from, it actually depends on, okay, W0 and M1 are also adjacent to each other because basically W0 prefers M1 over M0, or rather W0 is M1 successor. Again, W1 and M1 are matched pairs, so there is an edge. From W1 again you have an edge to M2 because W1 is M2 successor pair and so on and so forth. That kind of a graph, okay? Okay. So, now to see this, why this is true, look at the two matchings, the man optimal matching and the woman optimal matching, and look at their symmetric difference. Do you know what a symmetric difference is? See which edges are in common in them, discard them. Just retain the edges, basically those edges that are either in mu but not in mu prime and in mu prime but not in mu. If you familiarize yourself with symmetric difference as a matching operation, this is where all the bodies are buried. Like it's hard to find a matching proof and argument that does not use symmetric difference in some meaningful way, okay. So that's the thing. So in this graph, you know what, that because there are two stable, this symmetric difference captures precisely those edges that are different between mu and mu prime. We have already said the woman optimal stable matching is better for the women than the man optimal stable matching. Now can you infer a successor relationship looking at this in this symmetric difference graph? You will find the rotation to be existing in that graph itself, okay. So that's how we prove that such a rotation, at least one such rotation exists, and maybe they can be multiple, okay. All right. So in this particular example that we just now saw before, I can point out this M1, these three people, like these three pairs, M1 and his partner, M2 and his partner, M4 and his partner, they form a rotation. And you can see it, M1 is pointing to W3 as its current partner, right. W3's current partner is M2. Now we look at the successor of M2, it is W6. W6's current partner is M4. Now we go to M4 and see, well, M4's successor partner is W8 and W8 and M4, W8's current partner is M1. So we are back to M1, right. And there is another rotation which is this red one involving two pairs M3 and this thing M3 and M6 and its partners, okay. All right, and this is with respect to the matching mu1. I mean, I use the same table, right, as we saw before.
A rotation or a cycle in our case of 2 men and 2 women means in 2 sets, why that is not considered as blocking pair?
Sorry, why are the pairs in the rotation not considered blocking pair?
Yeah, if the cycle is for 2 men and 2 women, let's say I make.
So, like this this example where
That we have a.
that red one,
Yeah.
like this M3W5, M6W1.
Yeah. Why this is not considered as blocking pair? Because it is just like a rotation.
What would be considered a blocking pair? So M3W5 is part of a matching that by definition is stable, right? We chose that mu1 is a stable matching. So mu1 cannot have any blocking pairs. So if I just look at the rotation rho 2, which is basically just a subset of the matching edges, with some additional properties, right? But it's still a subset of matching edges. It cannot have blocking pairs because the bigger matching does not have any blocking pairs, right? And if I switch them around, like give M3 W1 as its new partner and W5 as M6 as the new partner, again they cannot be a blocking pair because all the women are strictly improving. W5 likes M6 more than M3. So when you switch along the rotation, as I just mentioned this a while ago, but it's worth repeating again and again, every single woman improves. Therefore, to have a blocking pair, you need a man-woman pair to like each other more than what they were before.
Okay, so the issue of women is improving before man is
Yes.
that's why it's not.
Yes.
Okay.
Okay? All right. So, now the question is, rotation, this definition makes sense. I can see there can be some benefit in it. How to find it? Okay? We find it, it's a very straightforward step. You basically, you take every man who has a different partner in a man optimal and a woman optimal stable matching. How do we find such men? Quickly, tell me. You can run Gale-Shapley from the men's side, man proposing Gale-Shapley, and you can run the same algorithm from the women's side, right, where the women are proposing. Interesting thought. And you see the people who have different outcomes in the two matchings, and these are the only people you consider. Okay? People who have the exact same partner in the man optimal and woman optimal stable matching, they cannot be part of any rotation. Try and see why this is. If you can prove the previous result that we were just now briefly discussing, you can also see this. Okay. Now, so clearly we know that because the dominance property, the man, a man will prefer any stable matching more than the woman optimal stable matching, right? Because that is the thing, that woman optimal stable matching is the uniquely worst stable matching from the man's perspective. So now, because of this condition alone, we know that with respect to mu, there exists the successor function can be defined. So for every man who has a different partner is the man optimal stable matching and a woman optimal stable matching, his GS list consists at least one woman who likes him more than her current partner. At the very least, it is his woman optimal stable matching partner. Maybe it could be somebody else, but at least she is there, right? So the successor person must be somewhere in between, either this last person or somewhere in between. So that at least the successor function is defined. Now, since the successor function exists, the next function also exists, right? The next is basically I should not say next function exists, the function obviously exists, but the next function when applied, it has an argument, it's not a non-empty this thing, right? Okay. So, because the successor exists, her current partner is the next, gives me the next function. So, M prime exists, M prime is the partner. Now, so why am I doing this? Okay, all right. So now skip step 4. Okay. Suppose step 4 is basically just restating what I have already said. So you can skip step 4. Now what I do is I now create a digraph where every man is pointing to his next partner. That next function, next points to a man in the somewhere who is basically the current partner of his successor, right? So every man gives a directed arc out to his successor, okay, to the current partner of the successor. So using this matching mu1, for all those men who have different partners in the in the current matching mu and the woman optimal matching, I do this. I basically give an arc from M to the next of M, okay. So this is a simple enough directed graph. In this graph, I see if there is a cycle. Can you find the cycles in this directed graph? Anybody? DFA? Yes, any of those graph exploration that would actually reveal a cycle. Notice this is a particularly sparse and a very simple graph. Every vertex has an out degree 1, like there's only one edge going out because your next function is uniquely defined, right? And in that, so basically when you have this property that out degree is at most 1 and now in degree could be more than 1, as we saw in that example. Like one man can be multiple people's next partner, right? Depends on how much his partner has to, his female partner has to be all those men's successor. That's possible. So you can have more in degree, but out degree is always at most 1, okay? So in this sort of a situation, can you tell me what the graph will look like? Like what does it consist of? What is a reverse tree?
Okay, I'm making a terminology. I'm not saying it's a.
Okay, describe what is that object?
Okay, what happens is that we have a node, we have multiple children. This time we have multiple parents but one children kind of thing.
Okay, okay, yeah, fine. The thing is, you can have things like this. The in branch, the in degree, what you were saying that multiple, you can have multiple parents and so on. So this is this thing, the vertex. So these are labels of the men basically. This is indicating man 7 has two people, man M5 and M8, both of them consider M7 to be their next. Okay, so that's what this 2 edges is. And you can have cycles. So in this graph, it's a very straightforward graph in which it's a very sparse graph. That's why, I mean, you can find cycles rather easily. Once you find a cycle, that's your rotation. If you find multiple cycles, you have multiple rotations exposed in this matching. Okay? So we know at least that in polynomial time, we can find rotations in any given matching, right? Now quickly tell me, how many rotations can there be in a given instance? Huh? N by 2? M? N by, why n by 2? Okay, but a man can participate in multiple rotations, no? Not in the same matching, but in different matchings. Oh, I said a rotation is defined with respect to a given matching. But when I say how many rotations can there be, I'm talking about rotations everywhere. But you're right, if that's what you interpret the question, that's correct. At a time, then you can have at most n by 2 rotations. Why is that? Because you need at least 2 men to have a cycle, right? Okay, fine. Now can you tell me how many rotations can you have overall? Quickly. Number of possible stable matchings. See the sorry? Why n by 2? Okay, in one given matching, there can be n by 2 rotations, at most n by 2 rotations. We agree, right? Like it's like everybody is participating in a rotation. You need at least 2 people, 2 men to have a rotation, so they can be n by 2. But overall, like across all possible stable matchings, there can be exponential number of stable matchings. But notice one thing, for a rotation to happen, the man has to have a partner, right? For every man, there are only n female partners. So a man can participate in at most n of different rotations involving this partner. Now, involving it, okay, now let's take a step backwards. Can the same matching pair participate in multiple rotations? How? So for example, I am saying if suppose M0, W0 are matched in some matching mu, can they be part of multiple distinct rotations. So rho 1 as well as rho 2. And if you, sorry? Why is that? Wait a minute, huh?
So if you look at the sequence of next, it will come back at a point if it comes back.
Yes.
That will change.
So why can't I have one man but having 2 cycles going through him? Correct. At least in one given matching, you cannot have a man participating in multiple rotations, because for that to happen, you need at least 2 outgoing arcs, and he has only 1 outgoing arc, right? At least in one single matching, you cannot have non-vertex, all rotations are vertex disjoint in a given matching, correct? That was this thing. Now, can it be the case, however, that M0 W0 is part of a rotation in mu1 and is also part of a rotation in some other matching mu2, and those rotations are distinct? Can you think of an example? Yes. Just because it has a unique partner, meaning, so the rotation is defined with respect to a matching, right? So if my matching changes, I can have distinct partners. But for the same pair to be participating, so I suppose what you're trying to say is, for the same pair, M0, W0 for example, to be participating in multiple rotations, multiple different rotations, right? It would have to be, so it would have to be participated, and those, and we just now saw that those 2 rotations can't be exposed simultaneously in the same matching. So can there be a matching M1 where this rotation exists, rho 1, and another matching mu2 where another rotation R2 exists that contains the same M0 W0? Can that happen? So try and see whether this is possible, and once you know this, you should be able to come up with an upper bound. Where is Devang? He's not here. Okay, he has a question about this, so I don't want to give out the answer. This is a good food for thought, okay? So try to think about this. So now, for rotation, there are lots. How much am I doing time-wise? Okay, almost ran out of time, but I'm really glad, running a little bit short of time, that you guys are at least responding to this whole thing about rotation, so that's at least time well spent. So now, this property that if you have a rotation, then any woman who is strictly between, so we know that each of the adjacent pairs consists of a woman who is this man's successor, right? That's how the rotation, this thing is defined. Now, in this case, this property says that between my current partner and my successor partner, all the women that are there, right, they cannot be a stable matching. They can never be part of a stable matching. Why is this obvious, or should be obvious? Again, we go back to the GS list property. The GS list at any time keeps the current matching partner and the successor. So all the women who lie between the current partner and the successor have already been dropped. And due to the robustness of the extended Gale-Shapley, we know that all the stable matching partners are in the GS list, and nothing is there among those people, that the pairs that have been dropped. So this holds from that case also. This also has a direct proof using simply rotation and not GS extend. So these properties have multiple ways of proving, okay? So this is at least one thing that should be like simple given what we have seen before. So this is somewhat interesting, and it leads to a lot of other consequences, and some of it we might be able to see, which is that if M again has a different partner in M and MZ is a woman optimal matching, then M leads to exactly one exposed rotation. So leads means you're either in a rotation, so the case that we just now talked about, or you are in the tail of a rotation, which is like you have a path going through, you're part of a path and then a cycle exists. You're not part of a cycle, but you're in the tail of that cycle. Okay? So there was a figure there, this sort of a thing. So these people, man 8, man 7, man 5, they are basically leading to this rotation. This is the cycle here. Okay? I hope you can see. This is the rotation and these are the people who are leading to this. Now it turns out at any given time you can lead to at most one rotation. So it's not just that you can belong to at most one rotation, but you can also lead to at most one rotation. Okay? All right. If rho is exposed in the matching mu and m is a man on a tail of rho in this Hesse diagram, this is called an Hesse diagram, okay, then this pair m comma w cannot be a stable pair if again W is strictly between the matched partner of M and the successor of M. Okay? So this, the property that we were talking about in terms of the people who are actually participating in the rotation, that is, you cannot be paired with any woman who is between your current partner and your successor partner in any stable matching. That condition holds not only for people who are participating in the cycle, but also those who are in the tail of the cycle. Okay? All right. So now, okay, if not, these things don't make as much sense, let's just move on and then we'll see why some of these things are important. Okay? So now we suppose we have, now what did we do? So we have already actually talked about this a while ago, which is that why are we talking about rotation? Rotations allow us to generate other stable matchings. You just switch along the rotation, the cycle, just give M0 his successor partner, the successor, the next partner gets his successor and so on. You just switch around the cycle, you get a different match, stable matching. And the stable matching has the nice property that everybody who is outside that cycle, meaning outside that rotation, have the exact same partner. Only the men and women who are participating in the rotation get a different partner. And as we just now saw, every man in that rotation gets a strictly worse partner, his outcome goes down, the women, they improve. So from this matching, by eliminating a rotation, we basically move a step closer to the woman optimal stable matching. Okay? Okay, so this is the, and this is what it means by dominated, right? The men get worse, so mu is dominating the matching you get by eliminating rho. So mu slash rho basically is the rotation you get by eliminating rho from mu. Okay. So this we have already seen. So anyways, okay. So given that instance that we saw before, that big list with the GS list and so on, it can have seven, 8 stable matchings from starting from M0 to M7. And the edge labels there, those rho 0, rho 1, those are the rotations. So you don't have to read this thing. These are sort of confusing way of this thing, but okay, forget it. But just take for me this thing that there are 8 stable matchings, but there are only 5 rotations, rho 0 to rho 4. Okay? So far, did we gain anything? We said we wanted to do algorithm on stable matching instance. Stable matchings are far too many, they are exponentially in number. Well, we still don't know how many rotations there can be, right? So maybe they are just as many as stable matching. So why are we doing all of this, right? So just you have to wait like a few more minutes and the answer will be clear. So now what we will show is that there is a very deep bijective correspondence between the set of stable matchings and subsets of rotations. So it's In particular, we can say that every stable matching has a one-to-one correspondence with a carefully chosen subset of rotations. So if you want to find a property about stable matching, this bijective correspondence, what does it give? It allows us to rephrase the question about stable matching purely in terms of these rotation objects, which are cycles on sparse graphs and so on and so forth. Okay? And so that the hope is that this itself gives us much more algorithmic tool to basically analyze. In particular, we also have all those structural properties, and I just listed a few. Those structural properties, if used properly, can actually allow us to answer meaningful questions about stable matching, which otherwise, if we just try to look in the world of stable matching, it may not be possible. Okay? Okay. Now, the precedence relation on the stable matching is we have been talking about so far, right? The dominance property, that here M0 dominates M1 because every man prefers M0 at least as much as M1, because they either have the exact, M0 is a man optimal stable matching, so there is no sort of arguments to be had. Notice M1 and M2, okay? So M2 is dominated by M1. This is what this arc means, that rotation rho 1 is exposed in mu 1, and after eliminating it, I get this matching mu 2. So what is the relationship between mu 1 and mu 2? Either a pair is in the rotation rho 1 or it isn't. If it is not in the rotation rho 1, then it has the exact same outcome in the two matchings, right? So there is nothing to. And if it's there in rho 1, all of those men have a strictly inferior outcome in M1. Hence, M1 dominates M2. And similarly, we can infer this precedence property for everybody, right? If rho 2 is also a rotation, this notation means rho 1 and rho 2 are simultaneously exposed in the matching mu 1. If I eliminate rho 1, I get to mu 2. If I eliminate rho 2, I get to mu 3. Okay? Notice something. We said that rho 1 and rho 2 are vertex disjoint, right? So I eliminate rho 1 from M1 and I get to M2. Rho 2 is still there. Rho 2 is now a rotation which is still exposed in mu 2. Correct? So now I can eliminate rho 2 and I get to a matching mu 4. Similarly, if I had gone down this path and I had eliminated rho 2 and not rho 1, I would have gotten to mu 3. But in mu 3, rho 1 is still exposed for the same logic as before. So now if I eliminate rho 1 from mu 3, I am actually going to end up at mu 4. So there are multiple ways to get to mu 4, depending on the ordering that you choose. But if I look at the subsets of rotations that are eliminated, they are all the same. So from mu 0 I came to mu 1 by eliminating rho 0. Then basically along this chain I get rho 0, rho 1, rho 2, and along this chain also I get rho 0, rho 1, rho 2. Right? The labels on these paths might be different, but as a like the ordering of the labels might be different, but you see the exact same labels. Okay? So when such a thing happens, when two matchings lie on a path that might start from somewhere but contains both of them, they are said to be on a chain. If you have two matchings that are not part of the same chain, they are incomparable. Example, mu 2 and mu 3. Okay? So, and then of course, now interestingly here, once you have exposed and eliminated rho 2 in mu 3, a new rotation comes to play, rho 3. So instead of, in mu 3, I basically have two rotations, one that was already exposed from a previous step, rho 1, and a newly exposed rotation, rho 3. At this step, I can either again eliminate rho 1 or rho 3. If I eliminate rho 1, I would end up at mu 4, like we just discussed. else if I just eliminate row 3 and ignore row 1 for a minute, I am going to end up at mu 5. Can you all see this? I am so sorry. Okay, mu 5. But then again, mu 5 still has row 1 exposed. Nobody has touched row 1 yet. So now I can finally again eliminate row 1 and I end up at this matching mu 6, right. Now notice row 3, this relationship tells me that row 3 is exposed after row 0 and row 2 are exposed. See how I got to row 3. There was row 0 at the very first step, then row 2, right. So no matter which matching I am in, as long as I have eliminated row 0 and row 2, row 3 will become exposed. This is why row 3 becomes exposed in mu 4. Okay? And so now I can eliminate row 3 and from M4 I get to M6. I am sorry, I am using M6 and mu interchangeably. So like, oh, these numbers are basically saying what the matchings are, but we do not need it. All we are talking about are the precedence relation and ordering. Okay. These are basically telling us which M3 is, man 1 is basically matched to W3. That is what this is saying. In M6, man 1 is matched to W3, M2 is matched to W6 and so on. That is not relevant for us at the moment. And then finally, row 4 becomes exposed. Okay. So row 4 will not be exposed. This diagram tells us that row 4 is only seen after row 0, row 1, row 2, row 3 are exposed. Okay. This sort of ordering, where some rotations only become exposed when certain other rotations have already been eliminated, gives us a precedence ordering on the rotations. So, I do not want to give this sort of a symbolic and notational definition, but this is what this is. This is how we infer the precedence rotation, precedence relationship on rotations. So, and this results in this. So, row 0 comes before everything. It is the rotation that was exposed in the man optimal stable matching. That is what got us going. From once row 0 was eliminated, we got M1 and both rotation row 1 and row 2 became exposed. See, they are simultaneously exposed. From row 1, after eliminating row 2, immediately row 3 becomes exposed, right. And once both row 1, all 3, row 1, row 2 and row 3 along with row 0 have been eliminated, that is when row 4 becomes exposed. So, from that partial ordering on the matchings given by the dominance property, we can infer a partial ordering on the rotations. Okay? Or you do not want to think about partial ordering, it is fine. Just think of them as precedence ordering. Like you can't just get to any rotation at any step. There are certain rotations that you need to eliminate before certain other rotations can be attained. Okay? Sorry. What is happening? Oops, this, it's not the same thing. Okay. So, quickly, a partial ordering on a set is defined along with a relation. This is a successor relation, this is the notation, you can have anything. A relation can be your name, it does not matter. It is basically just a mathematical object which tells us how to compare two items. Okay? So, and it satisfies 3 properties: reflexivity, antisymmetry and transitivity. And it should be fairly clear that our rotation and the stable matching, they all satisfy these 3 properties. That is why we call them partial ordering. Okay? Okay. Now, what we want is, so basically we obtain the partial ordering on the rotations via the partial ordering on the matchings. It turns out there is something very sort of like there is a huge bit of correspondence there. So, from rotations I can actually go back to the stable matching. Like if I just had the rotation poset, like rotation partial ordering, I could infer what the stable matching lattice would look like. That is the mysterious part. I mean, that's the part that the rotation literally was defined with respect to the matchings, right. We saw exposing and elimination of rotation happens because of the matchings. So, the fact that from the matchings you can go have a relation, the partial ordering on the matchings induces a partial ordering on the set of rotation is not surprising, that is almost constructive. The point is the other way around, how we define property on rotation and can infer the entire stable matching lattice from that. Okay. Now, so what is that relation? So, we will work with this example, okay, and so this is the stable this is the rotation poset we are. I am going to define an object called downward closed subset. Subset is a subset of rotation which has this particular property. You take any rotation here, let us say for this rho 1, and you take in this set, for this to be a closed subset, you have to take every rotation that precedes it. Okay? So, to have rho 1 in my rotation in a closed subset, I need to take rho 0. Can you tell me what should be the closed subset that contains rho 2? Correct. So, this would be the. Now, notice something, I am not saying anything about what comes after. You can have other closed subset that contain rho 2 and something that succeeds rho 2. The constraint is everything that comes before must be included. Okay? So, it is called downward closed, closed in the sense of transitive closure, if you are familiar with this. It is like I see all those vertices in this directed graph, the poset ordering induces a directed graph property, directed edges, and from rho 2 I am seeing all those vertices that can reach me via a directed path. Those are part of the closed subset. Okay? And of course, this is the smallest closed subset that contains rho 2. Anything additional you increase will give you other closed subset that contain rho 2, but this is the smallest closed subset. Okay. What is the closed subset containing both rho 1 and rho 2? I am saying a closed subset that contains both rho 1 and rho 2. Yes, you have to have this thing. That would be. Can you tell me what is a closed subset containing rho 3? Right. I do not even have to look at rho 1. I actually should not look at, if I include rho 1, that would be another closed subset, but at the very least I must include rho 2 and rho 0. So, you guys get the picture, good. So, if I just list out like this, you will see that these are basically the closed subsets of rotation. Rho 0 alone, it is a closed subset obviously, rho 0, rho 1, rho 0, rho 2 and so on. Okay. Now comes the sort of meat on the bones. There is a one-to-one correspondence between the closed subsets of pi of m is the rotation, okay, and the stable matching of m. So, for every closed subset of rotation you find, there is a corresponding uniquely defined stable matching, and the converse also holds. For every stable matching, there is a uniquely defined closed subset of rotations, such that if you eliminate that subset of rotations in the order in which they are exposed, obviously, you will get this matching. Okay, so this is the illustration of this. Wait, okay. This is what yeah. So, all right. So, let us see. So, with rho 0, it is like starting from mu 0, yes, mu 0 is the unknown, the man optimal matching within which rho 0 was exposed. If I just eliminate rho 0, I would have gotten matching mu 1. if I had eliminated row 0 and row 1, I would get matching M2. If I had eliminated row 0 and row 2, I would get mu 3 and so on. Okay? So, for each of this you can see that I will get 7 stable matchings because there are 7 closed subsets of rotations. So, this is the second property, which is that take any matching, let us start with this. Okay, let us read this. So, S is the closed set of rotation of the rotation poset corresponding to a stable matching M. If and only, so we know that there exists such a unique correspondence. So, for a closed subset of rotation, take the matching that it corresponds to. This means that S is the unique set of rotations on every M0 chain. M0 is the man optimum stable matching, this one, M0. So, every chain that starts with M0 and ends at that matching will contain the exact same rotations. So, let us take an example. What is happening? So, M2 for example, it somehow magically changes color, black or red, I do not know how. Okay. So, M2, how many paths are there to M2 from M0? Correct. So, there is nothing. So, row 0 and row 1 are the unique closed subset of rotation that corresponds to M2. What about M4? Right. See, these are distinct paths in the sense that they basically see different matchings on the paths, right. But if I just picked up the labels of the edges and ignore these vertices, right, the edge labels are here are the rotations, I get 2 paths with the exact same edge labels. This is what it means that every maximal M0 chain ending at this matching will contain the exact same labels, and the labels are rotation. So, you will see the exact same set of rotations. And what subset of rotation they are? It is that closed subset of rotation that it corresponds to. Okay. And yes, and you already know that we can generate this matching M4 by eliminating these rotations in the order in which they appear. And this is the other property. So, S and S prime are suppose let us say 2 closed subsets of rotations such that, and they correspond to distinct matching M and M prime. Just by looking at the inclusion property of S and S prime, if S is a strictly contained subset of S prime, then we know that the matching corresponding to S is strictly better for the men than the matching corresponding to S prime. So, any questions so far? I'll try to wrap this up, what we did and why we are doing all this. Any questions so far? So, what this does is allow us, as I said before, to completely interpret any questions about stable matching in terms of subsets of rotations. Now, this is not the end of it. There are very sparse graphs, that directed graphs that capture rotation, the precedence, the ordering on the rotation post set. Sparse graph means graphs that do not have too many edges, like they are linear in the number of vertices. Doing algorithm there is easier in terms of time complexity and likely to be more efficient than doing it in a more dense graph, for instance. So, that promises, at least is a potential, that some of these matching questions, stable matching question, if we just looked at the distributive lattice, would take more time than if we interpreted them in terms of the rotation problem. Okay? That gives a completely different characterization of these things. So, this is the example. If you work this out, you will see this is what. So, now we come to the final this thing. So, what just happened, right? I still haven't heard the question. When I asked them what is the number of rotations you can have, maximum number of rotations in an instant, they are still thinking. I have not given out the answers, but I am about to, because I need to. Otherwise, the story does not end.
The last slide.
Okay.
Can you quickly give a recapitulation of what was the row 1 here?
Rho 0 is the rotation exposed in the man optimal stable matching. M0 is the man optimal stable matching. Rho 0 is the unique rotation exposed there. So, the only way I can get to another matching is basically by eliminating rho 0. When I eliminate rho 0, I get a matching mu M1. M1 contains not one but two rotations. Those are rho 1 and rho 2. Is the figure clear? Is it okay?
So when rotation is happening at 5, 3, 8, 6, those are the M1 is matched to W5, M2 to W3 like that.
Sorry, say that again.
In M0,
Yeah.
we have this number 5, 3, 8, 6, 7, 1.
Yeah,
2,
this
4.
just says man 1 is matched to women 5. Man 2 is matched to women 3 and so on.
And below like 1, 2, 1, 6.
Oh, this is basically the rank of these women. So, M1 is matched to his first partner, the top rank partner, that meaning rank 1 partner. M2 is matched to W3 who happens to be his second rank partner. You will, as you can see, the men, what their rank value is as the rotation gets eliminated, man 1 was initially matched to his top partner, right. It becomes 6 after elimination of rotation rho 0. After elimination of rho 1, man 1 goes down to his 8th partner. This is the last partner in his preference list. For man 2, he goes from being matched to his second partner to his 8th partner. So, you can see as you go down the chain, the men are actually going down. Okay. So, the good question actually, that is what these numbers indicate. Okay. So, what just happened? What happened is this following. Okay. So, let us recap and add more sort of layers to what we just now learned. So, the set of stable, from the set of stable matchings, by eliminating, exposing and eliminating rotations, we get a partial ordering on rotations, right. Literally that was ordering, the order in which they get exposed. This leads to these objects or chains, rather the directed paths. Chains are basically the matchings or the rotation that appear on a directed path. If two objects do not appear on any directed path, they are supposed to be on an anti-chain. Okay? So, that is the thing. Think of it as a directed path or anti-path. Give your own name if you do not like chains and anti-chain. The chains allow us to define the downward closed subsets of rotations. We did, right? You stand at a rotation and see who all can actually have a directed path to you. That consists of the smallest closed subset that contains me, this particular vertex that I am standing to. This, the last bit of slide basically shows this one-to-one correspondence. Like this direction, I would say this portion is, this arrow is constructive. This side uses what property? That one-to-one unique correspondence property. Okay? All right. Now, from the chains and anti-chains, you can define this object which is we call rotation digraphs. It is a even more sparsified version of the rotation graph that you just now saw a while ago with those directions coming. That captures all the essential precedence relation, but might have even fewer edges. And Pallavi will address that in her talk. Okay, so you'll hear about that more. Now, here comes this thing. If I just ignore all of this, just knowing the rotation digraph and knowing this property, I have a way of, in the rotation digraph, I can look at the downward. So, downward closed subset of rotation is basically literally the transitive closure, like the vertices that can have a directed path to me. From here, we have this, from knowing downward closed subset of this object is happening in the partial ordering of the rotation, This is a sparsified object that does not contain all the relation, but still captures all the reachability properties. That is what this equivalence is. This one side obviously is true. This has all the edges that are there here. So, one would imply this, but the other direction is the interesting part. Okay? So, I think Pallavi will address that briefly. And okay, the transitive closure is via that. Okay, fine. I think you guys get. Now, the issue is, as we have already said, stable matchings can be too many, exponential, c power n. There can only be order n square rotations. And the rotation digraph, okay, can have, sorry, this is wrong. It can have order n square vertices corresponding to n square possible rotation, and the number of arcs is also order n square. This is wrong. What I was trying to say, it can be linear. Okay? So, same number of vertices and arcs, I mean asymptotically. This allows us to do, as I said, we infer every question on stable matching in terms of rotation and work with this very efficiently computable, sparsely representable, very easy to work with, like low overhead, low space overhead object. And this is where all the efficient algorithms come into play. Every non-trivial algorithm about stable matching that I can think of since the 1980s, late 80s, has used rotations. Such is the power of this mathematical object called rotation, the closure property of rotation diagrams. Okay? So, with that I end.